We have started. We have a launch failure later, almost 50 years of amazing space exploration. NASA's Explorer spacecraft confronted a basic glitch, imperiling its inestimable route. A group of splendid researchers and architects was gathered by NASA to perform an exact system update and set Explorer 1 on its course. Now, something bizarre just occurred after the completion of the system update that has terrified researchers across the world. What stunning discovery did NASA find in the recently stored data? Could this be proof of extraterrestrials? We should figure out what happened after Explorer 1 received a programming update 15 billion miles away in space. Imagine the farthest man-made spaceship from Earth encountering a breakdown with no current playbook for resolving the issue. This was exactly the situation faced by NASA, prompting them to devise a brilliant plan. NASA released a task posting for computer programmers with a specific range of skills. These developers had to be experts in Fortran and assembly, two programming languages from the 1940s and 1950s that are new to most recent graduates. NASA formed a group of scientists tasked with a total redesign of Explorer 1's system all the way from its location, 15 billion miles away. For over half a month, the team conducted extensive research and re-engineering, considering the extraordinary alterations that had been made to Explorer 1 since its launch in the 1970s. After finishing the update, NASA researchers made an astounding revelation, a neglected arrangement of data that the spacecraft hadn't sent in years. Something unusual just occurred after Explorer 1 received a programming update 15 billion miles away. However, to see precisely how this could happen, we need to consider some context. During the 1960s, an extraordinary proposition emerged, a daring drive to undertake a grand endeavor across various planets, venturing into the mysterious realms of the outer planets situated in the vast expanse of our solar system. This ambitious endeavor, aptly named the Grand Tour, sought to launch automated missions to explore Jupiter, Saturn, Uranus, Neptune, and even Pluto. What made this plan truly remarkable was the unique alignment of these planets, a rare event that would grace the universe in the late 1970s and not be repeated for another 176 years. Exploiting this celestial arrangement, NASA's Voyager spacecraft, Voyager 1 and Voyager 2, were successfully launched in 1977. The goal was to use the gravitational pull of Jupiter as a slingshot, propelling them on a long trajectory to the outer realms of our planetary system. Initially, the primary objective of the spacecraft was to unravel the mysteries of Jupiter and Saturn. However, their amazing discoveries compelled an expansion of their mission boundaries. With newfound resolve, Voyager 2 embarked on a historic journey, venturing further into space to explore Uranus and Neptune in remarkable achievements that remain unmatched by any other spacecraft to this day. Innovative control programming blessed the Voyager missions with enhanced capabilities, exceeding their original potential over time. Voyager 1 and Voyager 2 undertook a magnificent odyssey, exploring all the major outer planets of our solar system, meticulously analyzing 8 of their captivating moons and unraveling the intricate systems of rings and magnetic fields that these celestial giants possess. In December 1977, Voyager 2 entered the asteroid belt, while Voyager 1 navigated at a swifter speed, surpassing its companion. 9 days later, February 1998 marked a great milestone for Voyager 1 as it surpassed Pioneer 10, becoming the most distant human-made object in the vastness of outer space. In 2002, Voyager 1 departed from the nearby planetary group, rising above the ecliptic plane at a striking angle of 35 degrees, moving forward at a remarkable speed of 39,000 miles per hour. Voyager 2, on the other hand, charted a unique course, slipping beneath the ecliptic plane and progressing at a notable angle of 48 degrees and a speed of 3,450 miles per hour. Voyager 2 holds the record for visiting more planets than any other man-made spacecraft, while Voyager 1 proudly rules as the most intrepid explorer from Earth, journeying further from its point of origin than any other craft. Remarkably, both Voyager 1 and Voyager 2 completed their exploration of the outer planets within the first 12 years of their groundbreaking mission, having fulfilled their primary objectives by 1989. These fearless explorers stood ready to embark on a new chapter, investigating realms beyond the limits of our solar system. In January 1990, with their sights set on destinations far beyond the local planetary group, the mission's assignment was aptly renamed the Voyager Interstellar Mission. Thus, these dauntless Voyagers continue to wander into strange domains where no biological creation has ever ventured. Voyager 1 is no ordinary spacecraft, it is an exceptional testament to the creativity of NASA's brilliant engineers, challenging the relentless passage of time with unparalleled precision. This interstellar pioneer boasts a striking array of features that have facilitated its journey through the universe for nearly 50 years. Among its many remarkable attributes is its robust radio communication system, meticulously designed to function even beyond the celestial limits of our solar system. At its core lies a massive 37-meter high-gain dish antenna, serving as the crucial conductor for transmitting and receiving radio waves across the vast distance between Voyager 1 and our home planet, through the Deep Space Network stations. When direct communication becomes impractical, Voyager 1 relies on its reliable digital tape recorder, DTR, capable of storing around 67 megabytes of data for subsequent transmission. To put this achievement into perspective, signals from Voyager 1, as of 2023, endure a stunning 22-hour journey through the depths of space to reach Earth, a moving testament to the vastness of the universe. Equipped with sophisticated cameras, Voyager 1 has the capacity to capture celestial wonders, documenting distant planets, their captivating moons, and realms beyond. Interestingly, these visible light cameras operate under the guidance of an imaging boundary table, carefully stored within one of the spacecraft's advanced computer components. While Voyager 1's camera system relies on preordained instructions, it is noteworthy that more contemporary space probes developed from the 1990s onward have adopted fully autonomous camera systems. In contrast to the traditional Voyager 1, which depends on its clever computer command system, CCS, to organize its tasks, this system, an engineering marvel from the 1970s, controls various spacecraft functions, including command decoding, fault detection routines, and antenna pointing schedules. Shuttle sequencing schedules, a redesigned variant of the CCS, first utilized during the 1970s Viking orbiters. It remains as a demonstration of the persevering force of strong engineering. Before we talk about what simply occurred after Explorer 1 got a product update, you would need to figure out what's behind the longevity of Explorer 1. What accounted for the progress of the Explorer tests? As you would anticipate, Explorer 1 and Explorer 2 rockets were outfitted with a great array of specific scientific instruments involving Intel suites and subsystems, which represent the longevity of the tests. Only a small handful of instruments continue to function on board these gutsy pioneers. One of the enduring instruments that remains functional on both Explorer 1 and Explorer 2 is the low-energy charged particle detector. This astounding gadget, equipped with 3 arrangements of particle sensors, investigates particles and determines their speed by steadily analyzing cosmic radiation and particles emanating from the Sun, planets, and interstellar space. This detector provides valuable insights into the composition and behavior of these cosmic substances wandering further into the realms of vastness. Both Explorer tests are equipped with an infinite beam instrument. This instrument, with its surprising ability to detect highly energetic particles originating from the Sun and other cosmic sources, currently serves a vital role. It measures the wealth of particles within the protective bubble of our Sun's influence, as well as those coming from interstellar space. These readings act as critical markers for researchers, supporting them in pinpointing the exact moment when Explorer 1 ventured into the vast expanse of interstellar space. Another essential instrument that continues to operate on both Explorer 1 and Explorer 2 is the plasma wave subsystem. Using its 2 elongated receiving wires, which extend at right angles to each other, this subsystem tirelessly measures the electrical field components of potential waves experienced during the test's operations. Initially expected to concentrate on these phenomena around the outer planets, the instrument has now assumed the role of unraveling the mysteries of plasma waves as they permeate interstellar space. Its active contribution in both spacecraft ensures an abundance of data for researchers to analyze and understand. Additionally, the magnetometer, initially tasked with examining the magnetic fields of the outer planets, has now transitioned into another domain of scientific inquiry. Its primary goal is to test the transition region between the interplanetary and interstellar media by examining the magnetic characteristics at the boundary where the Sun's magnetic influence gives way to the magnetic field of interstellar space. This instrument sheds light on the complex interactions between these cosmic forces. Explorer 1 and Explorer 2 also continue to rely on the plasma science instrument for vital data acquisition. This instrument energetically searches out the lowest energy particles within plasma while also having the ability to identify particles moving at specific speeds. Moreover, to a limited degree, it can ascertain the direction from which these particles originate. As the spacecraft embarks on its interstellar journey, the insights provided by this instrument become increasingly essential. While some instruments have succumbed to the ravages of time or have been purposefully deactivated to conserve power, the determined efforts of the Explorer team continue. Unnecessary instruments were permanently shut down in 1998, 21 years after the initial launch, in a bid to preserve resources. NASA has also deliberately deactivated radiators on both rockets as part of their power-saving strategy. The power source for each Explorer spacecraft lies in a group of 3 radioisotope thermoelectric generators, RTGs. These remarkable devices derive their power from the decay of radioactive plutonium-238, converting thermal energy into electricity. However, as the plutonium-238 continues to decay, a time will come when it can no longer support the instrument's power requirements, resulting in the cessation of all scientific operations. This inevitable power decline is projected to happen around 2025, but the Explorer team aims to extend the lifespan of both spacecraft until 2027. This date holds special significance, as it marks the 50th anniversary of their groundbreaking launch. To ensure continuous communication with Earth, each Explorer spacecraft is equipped with a couple of engines. These engines, although not intended for propulsion, play a crucial role. Job in reorienting the shuttle, guaranteeing that their receiving wires reliably highlight our home planet by radiating brief, however exact, heartbeats or puffs enduring simple milliseconds. These engines carefully change the rocket's position, empowering essential communication to be maintained. What ongoing glitch has grabbed the attention of researchers, and why did NASA settle on a software update recently? The famous Explorer 1 space apparatus has experienced a progression of upsetting difficulties that undermine its very presence. One of the pressing worries that have emerged is the event of confused or adulterated telemetry information. As Explorer 1 navigates huge distances, it depends on sending vital data back to Earth to keep researchers informed about its status. However, on several occasions, the sent information has shown up in a contorted and incoherent form, leaving researchers wrestling with the overwhelming task of interpreting its valid meaning. This peculiarity has represented a significant obstacle in grasping the rocket's current status and the climate it experiences on its interstellar journey. Compounding these communication challenges are the signs of maturing and crumbling that have appeared within Explorer 1's engines. These indispensable motors, responsible for reorienting the shuttle and ensuring its radio antenna remains pointed toward Earth, have begun to display indications of wear and glitch. As the engines falter, the delicate balance required to maintain steady communication with our planet becomes increasingly problematic. The risk of losing the ability to receive critical information from Explorer 1 lingers forebodingly, potentially cutting off our connection with this moving messenger of exploration. The ramifications of these issues extend beyond simple technical troubles. They could spell the destruction of Explorer 1, a rocket that has blown minds and surpassed its expected life expectancy. Without the capacity to send clear telemetry information, and without reliable engines to maintain its orientation, the fate of this exploring test remains in a precarious situation. The loss of Explorer 1 wouldn't just denote the end of an era, but would also deprive us of valuable insights into the mysteries of interstellar space. Notwithstanding these challenges, NASA set out on an energetic mission to overcome obstacles and extend the life expectancy of Explorer 1. They meticulously examined the jumbled telemetry data, utilizing modern algorithms and innovative strategies to extract significant information from the muddled signals. All the while, they explored alternative techniques to compensate for the faltering engines, diving into the possibility of using other onboard systems or concocting clever workarounds to keep the shuttle properly aligned toward Earth. One critical realization arose from their efforts: a system update was essential. In 2015, NASA put out a solicitation for a programmer with expert knowledge in Fortran and assembly, two programming languages that were popular during Explorer 1's initial launch. Updating the spacecraft's systems proved to be a daunting task, as both Explorer tests still relied on their original 50-year-old computers, equipped with only 70 kilobytes of memory. The engineers soon found that the engines responsible for maintaining Explorer's desired direction were showing signs of exhaustion. Each time the engines were engaged, microscopic particles of hydrogen fuel became trapped in the lines, slowly causing blockages within the system. Explorer had already progressed to its backup engines, and if these were to fail, it would mean certain doom for the space apparatus, with a staggering distance of 15 billion miles from Earth. Clearing the cylinders represented an outrageous challenge. By the way, the small team responsible for Explorer's prosperity embarked on an extraordinary endeavor. They began developing a programming update that would cross the vast field of our universe to rectify the issue. Explorer's onboard infrastructure includes 3 essential computers, each serving distinct functions. The primary computer took command over all major instruments, directing the spacecraft's overall health and temperature, while also managing the other 2 computers. The second computer focused on Explorer's navigation, diligently searching for predetermined reference points and activating the engines to ensure the antenna remained pointed at Earth. The third computer specialized in storing and handling the scientific data and images captured by Explorer's instruments.